As Simon has said, it has been a while since I was in a class lecture, a year ago, and I'm happy to talk to a group of people now again. And on top of that, I am an optometrist by profession, so I am a clinician. Again, I'm used to speaking to one person at a time when they come in the clinic. So, yeah. So, welcome so much. My name is Walter Yego. I'm a PhD candidate from the Department of Optometry, Radiography, and Lighting Design. So I'm going to present a little bit about my project, and I'm going to focus on eye and vision. All the three candidates, my fellow colleagues that have presented very great project. But I would like to emphasize that we use eye and vision to do all this in the best way. So we definitely know the continuum of virtual reality, from the real environment to the virtual environment. And my project is focusing on understanding individual differences in eye and vision in person using XR technologies. Because if we think about implementing virtual reality in a group of classroom, for example, we have people who may have vision problem, common eye problem. They may not be able to see very far, or they may not be able to see very near, or they may have the problem with coordination of the eyes. Yet we are implementing the same technologies for everyone. So the question of individual differences comes in. And my project is focusing at looking at these individual differences in the context of the eye and vision. So a little bit about the eye and how the eyes works. I promise I will make this very simple. So our eyes have ability to focus at an object which is at distance and an object which is at near, especially when you're looking at your phone. And when you are looking at distance, for example, in our picture there, the ability for you to focus an object or to look at an object clear and ability for the eyes to come together are usually similar, or we say are usually normal. In other words, we can say that our eyes are coming together at a point object while we are making clear that object. So we call that normal, what we see. So in this picture, the eyes are focusing at the object at the same point in space. Now that is when you're looking at distance. Now let's look at near. We look at our phones, and that's how our eyes are focusing. So in other words, we are saying that the neurological linkage, whatever is in the brain that coordinates these eyes, ensure that this is maintained. So what happens in 3D display, for example? The neurological linkage is broken in such a way that our eyes always have to focus at distance. And when we are focusing at distance, ability to make an object clear is usually limited by the 3D display. If we take, for example, HoloLens, a technology that has come from Microsoft, or virtual reality, they do have a focus distance of 2 meters. So you can make things clear at 2 meters. But where is the location of simulated object? It can be 10 meters or it can be much closer. So this is somebody who is looking at a distance object, and yet they are making an object clear at a distance that has green circle. Now when they look at near, a bit closer, the simulated object come a bit closer, but ability to focus this object still remain constant. Let them look a bit much closer, you will find out that the ability to focus, which is a green circle, will still remain at the same point, while the simulated object come much closer. So this is an area that we were interested to find out, why is this the case? So my project focused at to what degree are this ability to focus and ability to look at the simulated object affect different tasks. And at our first instance, we looked at executive functions, how we plan and implement a task, for example, in industry or something like that. And the first picture on the left is an example of executive task that we implemented. And we have so far tried to look at to what degree accommodation and divergence, which is basically making an object clear and bringing our eyes together, affects executive function in augmented reality. So therefore, we then developed an augmented reality task, virtual augmented reality task, and we implemented in one of the augmented reality device, which is HoloLens 2 from Microsoft. We then set ourselves to understand objective one, and we performed these experiments in the laboratory. We did normal clinical tests that you will find when you visit an optometrist or an eye doctor. And on top of that, we also did laboratory tests. Then we enjoyed the project from that, and we implemented the project. And as you can see, that is how it appears when someone is performing these tasks. So the task is called the Tower of London, and the participant was supposed to arrange the balls on the pegs according to the final results that was displayed 4 meters away from where they were. So they could hold they could hold the virtual Tower of London at a distance where they are comfortable, but the final results could be seen 4 meters away. So that's an example of participants who was performing the task, and the instructions were given step by step. Behind the scene, you can see the investigators. You may be able to have an idea about some of them. All right, so then we went ahead and did clinical tests together with laboratory tests with a view of understanding. So this is the most interesting part. We are in the process of data analysis after recruiting so far 18 participants that we are going on with more of experiments. And this is an experiment, this is the results of one participant when they are focusing at an object. So the red lines represent the expected focus at distance, that is at far, and also at near. While the boxes here represent how the participant did or performed. At the lower part on the x-axis, that is the lower part, we can see distance, near, distance, and near. And we can see we took these measurements before, and then they performed Tower of London, then we took these measurements after. And I must say that this is just one participant. And what was interesting about this participant, when we asked them to focus at distance, they were able to focus quite okay. And when we asked them to focus at near, they were able to focus almost to what probably, but just slightly above the red line. So what we were doing, we put them before an experiment, and we put an object at 4 meters, and we put another object at 40 centimeters. And we asked them to look at 4 meters, which is distance, then 40 centimeters. So they repeat like that for 1 minute. And they do that every 3 seconds. So that means 4 meters at distance, 4 meters at distance, 40 centimeters at near, every 3 seconds. So one cycle was 6 seconds for 1 minute. So before, they were happy because they were able to focus where we wanted. But after, let's look at the results after. When we asked them to look at distance, they were able to look at distance, but slightly behind the red line, slightly behind the expected. But what happens when we ask them to look at near? They were stuck, a little bit stuck, I could say stuck, in such a way that instead of bringing their focus to near, to almost red line at the bottom, they almost maintain their focus at the red line at the bottom, even though the instructions were clear and everything was clear. So this clearly tells us that there is something that is happening. And this could be me, it could be you, it could be somebody else, or it could be our children who are in virtual reality or augmented reality performing this kind of task. So we are saying that this is one case. Someone else, another case might perform differently, and another one might perform differently. And we are in the process of that analysis with an interest to observe whatever is going to happen. So we are keen on individual differences in this ability to focus and to bring our eyes together in different contexts. And this is a case of where the participants were performing executive tasks using Tower of London. So what next? We continue to analyze our data and to perform our experiments, and we look forward to sharing more results. Thank you.